now this session we will talk about the different ways you analyze all the electrodes together, because nowadays we measure not just from few locations but over a handful of locations, and from 16 channel, 20 channel, 30 channel, 32, 64 there. So it's kind of good reasonable spatial sampling over the scalp. So in addition to applying your measures or analysis at the individual electrode level, so we are also interested how we can analyze all the electrodes together. So the first, I already showed you these things. The one thing we often use, that any measures, even though we apply at a single electrode level, we want to see how this measure distributed over the scalp. So we shown from the first lecture, you call it scalp map. Principle is very simple. That you know which electrodes you're recording, and then at each time period or over a time period you estimate or you apply a method which gives you one value at each electrode, and then you put that value into that location, and then using interpolation technique you create a map which tells you about how this particular index, whether it's a peak amplitude, whether it's a mean amplitude or any other measures, how this particular measure of your choice distributed over the scalp. So that's the very first topographical analysis of EEG signal. We take it as granted, these things, but there are certain approximation. I'm not going into what kind of interpolation you need to do. That's not that much of interest. The other immediate measures that can be applied on the global level, we talked briefly about that. They're called gradient and current source density. The gradient is the first spatial derivative. So it is the degree of in the voltage measured at electrode X relative to its neighbor or set of neighbors. Because it's a difference and there is a direction involved, it's a vectors there mathematically. So it varies in strength and direction. But essentially you can also call it as a bipolar recording there. So you express voltage at one electrode with respect to the voltage of a nearby the current source density, or we call surface Laplacian. So this is the degree of change of the degree of change. So it is if the first one is more like speed, which is the degree of change in time distance, now is the change of the speed means acceleration metaphorically. So that's the current source density there, and so conceptually or mathematically it's very similar to as if you are applying a spatial high pass filter. And the big advantage of current source density is voltage you need 2 points to describe, but the current you can describe at any point. And the way it is constructed, you are de-emphasizing the contribution from the distant sources. So if you take a second derivative, you are accentuating very local or focal activities. And I think when we talk about this thing in the first talk about a couple of days back, someone asked you about how we calculate. I explained that, but then I found it this simple figure which explained very easy way. Suppose this is your voltage at any point distribution of how many electrodes, doesn't matter. So here, suppose you just plot the electrodes as a vector sequence, and at any point this one electrode at the left is 5 microvolt and 7 or 8, something like that. Now you have to measure the first derivative. First derivative is nothing but first difference. Suppose this electrode you are only measuring this one minus this one, or actually you can do this minus this, this minus this. So that's the first derivative at the first electrode. So just what you take, just subtract with the neighbor from its current value there. So this is the gradient there, and if you take the gradient, okay, another first derivative, then becomes the surface Laplacian or the second order there. So that's the very simple okay, formulation. Only thing is, in practice it's a slightly more complicated, because here what I am assuming, this electrode only has one neighbor here, but in the surface we know that one electrode, if we choose, it has many neighbors surrounding it there. So and accordingly we don't just subtract activity only from one neighbor, but from a group of neighbors, and depending on your selection of neighborhood, accordingly this subtraction would change, but the procedure is the same. You select a neighborhood, calculate the mean activity of the neighborhood, subtract this mean activity from your located or from your selected electrode, and do the same thing in the second round again. So that would give you this. So suppose this is your voltage scalp map, this is the first order gradient scalp map, and this is the second order current source density there. So what you primarily find, it's a kind of similar, only thing is, because it accentuates or the focal activity there. So if something happening at a very local range, by taking a second derivative, because second difference operator, it just emphasizes whether or any activity that is occurring or happening at a local level there. So by definition, current source density de-emphasizes any long range activities, emphasizes very local or activities which are at the surface level, and it has a lot of interesting properties as well, because essentially okay, it is reference free, because each electrode has their own reference there. That's an advantage, but the second kind of, or not say advantage, this is a corollary of that, means then the electrode at the edge which doesn't have a very good neighborhood there, because those electrodes are the boundary there, you cannot create a nice neighborhood around those electrodes. So your current source density approximation would be quite poor at the edge electrodes. And the third is, you need to have a reasonably high density electrode. Suppose if you use emotive and others, forget about using current source density, because it literally you have very few electrodes there. Another advantage, it will possibly come into later, that often when you want to use the or understand the brain network or synchrony, connectivity between different brain regions. So if you get a high connectivity, suppose between two electrode regions, okay, you can say this is a strong information exchange between these two electrode regions, but it is not certain, because often what happens, the both electrodes possibly picking up activity from a same source. You do not want to claim connectivity based on this information, because then it would negate your earlier finding. So what you want to do, in order to discriminate, you apply a current source density transformation on your data, and then you repeat your connectivity analysis. So if you do that, then whatever connectivity or strength of synchronization you'd get, that would eliminate the possibility of a contribution of a common source there. So this is, anyway, we are here still in the ERP domain. Connectivity, we will cover it later on there. So this is a nice way of describing the current source density, and I think it has a good potential, but some reason it is not that used as frequently as I think it should. So map descriptors. So if you consider, once you plot your voltages as a map, it's not like an image, right? Now how you want to characterize this image there. So the mapping is a kind of another way to interpolate and display the recorded EEG signals there. So it would be quite useful to somehow extract the features which are quite specific to the map, to the way your voltages are distributed there. Although one hand you think you are doing some data compression, that out of all the map you are using one descriptor, but you have to remember you are increasing the amount of data by mapping, because you are doing a lot of interpolation for the map there. Anyway, so the spatial configuration, you have to remember, of the EEG somehow reflects the activities of the distributed neural population that give rise to the EEG signals. Now, if you highlight or if you analyze only electrodes individually, then you do not have this information, what's happening, how globally things are happening, because your focus of window or analysis window on a very local electrode stage there. So by looking at changes of potential values of the ZRP only at isolated electrodes, it is almost impossible to infer whether these changes are caused by a global change of source strength or by change of source distribution there, means change at very locally there. So in order to address this, you have to consider the overall distribution of the voltages there. So that's the idea, that go from single channel analysis to the analysis at the global level. Quite a few descriptors are available there. I just highlighted a few which have been used, but again you can apply many others, a related index or index taken from the image processing actually can use here as well there. So some simple map descriptors there, which you can look at it in your map, where it is find the most positive and the negative values, very simple there. You can look at it at a different axis, so whether it's anterior, posterior, or left and right. So on this axis, on your Scalp map images, where the extreme potential values, and you can also monitor their temporal distribution, temporal evolution. You can also calculate, is a map centroid or positive or negative areas there. So suppose if given a simple formula, if UI is the voltage of the map at the ith electrode, and xi is the electrode location on the x-axis, and if you have n number of electrodes showing positive value, you can calculate the centroid of either positive or the negative areas, and for each map, and then you can compare it between two conditions there. Similar to the centroid, you can also calculate the electric gravity center there, which is very similar. You just take a modulus there. Suppose here I given a simple example here. So this is, I forgot which experiment it is, it's not my data. So that's the temporal profile of this electric gravity center there, and this is the stimulus onset. So 1 second. At some point you can see there is a 3 different axes there. So I think one axis at some point, here in this case 700 millisecond, whether you have to see whether that means something change in the global configurations there, and you can compare it between these two conditions there. Again, this is advantage of this thing is you do not have any specific hypothesis. These are exploratory analysis. So it is not ERP you are looking at N1 or P2. So all the map descriptors are very much exploratory there, because you let the to guide your analysis there. So you come up somehow approaching the data with an open mind there. This one more used is called global field power there. It's pretty simple here. So UI is again the same as the voltage of the electrode I, and this is the average of all the electrodes. Take the subtract, take it square, divided by the number of electrode. There it is nothing but literally the root mean square, means it's a spatial standard deviation there. So, at any moment in time, global field power would give you overall spatial standard deviation across the scalp there. So, it is a reference free measure there, and scalp potential fields, if the ERP has either if your global field potentials is high, so that means at that moment there will be steep gradients of the potential fields, either peak, positive peak or negative peak there. So, means different electrodes are doing slightly different things, because it's spatial standard deviation. You are checking at primarily how much the field the potentials vary over all your electrodes. So, if some focus activity on some channel showing strong ERP peak, other channels not, then you get a high standard deviation there. That is the idea. Or if there is not much of focused activity going on, then GFP would be low there. So, if there is only shallow gradients across your scalp map, then your global field power would be low there. So, means high global field power is associated with a stable landscape configuration, and low global field power changes with the configurations. And what you study usually global field power as a function of time. Some couple of points about global field power. I will show you some results. The global field power is essentially a nonlinear transformation, means ordering is important. So, if you means again the global field power at individual subject level, and then you take the average, it would be different from the global field power of the average brain signal there. And what global field power tells you is on average how strong a potential has been recorded across the electrode montage with respect to other electrodes there. But it does not tell you about how this potential is distributed across montage, because at any point you only get one value across all your 32 or 64. It tells you about the extent of distribution of the scalp potential over the scalp. So, this is given example, it is from our own study quite a few years back, just one to show, because here we are somehow because again it is an exploratory method. We wanted to find at what latency two conditions differ. So, this is details of the condition is not that important here. So, there is a condition 1 and condition 2. Actually, in this case, this is from the ERP point of view is a very good condition, because both in cases both condition subjects are looking at the identical stimuli. Only what happened beforehand, that is where the different. So, it is a comparing identical conditions. Only the priming was different. In one case, the subjects listened to one type of music, in other cases another type of music. So, and then this red one is the global field power for one type of prime, means when the subjects listen to a positive piece of music while they are looking at a neutral phase, and the blue one when the subjects listen to negative music and looking at the same phase there. And you can see the global field power at the very beginning they are very similar, but almost after 50 millisecond, which is reasonably fast, and this global field power started kind of showing the differences between the two conditions there. So, this is you can see here. Now, you can go back to your EEG signal and to check it out really whether you see any strong differences there. So, this is kind of again a kind of nice way of exploring your data there. Similar one, another one, this is from a different group actually there. So, they use the global field power to study the differences between and healthy group participants and someone who is a photic sneezers while they are exposed to photic stimuli. So, here what happened, this is the global field power of this patient group there, and that is the global field power of the healthy controls. I forgot the timing here, but this is an ERP paradigm, so it would be pretty close. Now, once they find the global field power and then they compare between this global field power, statistically compare, they found the earliest differences between the two groups were found here and also here. So, at the very early stages and the very later stages there. And then what they showed it here, because this is where kind of gives you which window to look at. Someone asked in the morning when you're talking about ERP, which window to look at. There we have guided by the previous literature if you target specific component, but here we have an exploratory approach. So now the data tells us, oh, okay, there are some interesting things happening here. If we apply proper statistics here, also some interesting difference between the group. And then after applying source reconstruction, we will cover a bit later on, they found this activity between the two groups are represented in these brain regions. Details are not important where it is. And similarly, you can apply source reconstruction here at this later stage. The other sort of brain regions are somehow coming up, showing different activities there. So this combining these two here, you can see, gives you a nice story there. So one helps us where to look at, and the other you are applying a different analysis to, because global field power doesn't tell you where in the brain. It tells you when something is happening, and happening at a global scale there. Then another index map descriptor called a global map dissimilarity there. So this is like you want to find out whether two topographical maps or scalp maps are similar or dissimilar. Okay, you have two conditions, you want to compare it, how similar or how dissimilar. So if you can compute this, because this is a UI is a one conditions and V is another condition. This is an average, and this is a GFP for global field power for condition 1, and this is for condition 2, and N is the number of electrodes. So if you can compute this, the way it is defined, that it would be 0 if the two scalp maps are identical there, and if the two maps are opposite, means condition 1, one map showing positive, condition 2, the same electrode is showing negative. So it's just a mirror image there. Then this value would be 2 there. So if 0 is for identical maps and 2 is with opposite polarities there. This also can be useful if you are interested in in finding the topographic differences between the two maps. I haven't seen, something that comes to my mind, that this also can be used possibly also as a classifier as well. If you are having a targeted classifier, and at every moment in time you can calculate the map there, so possibly you can also use it as how much different your current condition is from your target classifier. Just an idea, because it gives a summary of your how these two conditions differ at the overall global scalp level. Okay, that's good. I'm going a bit fast, so it's good that maybe after second half I'll keep it a question answer. Okay, global map dissimilarity. Usually it is GMD is inversely correlated with global field power there, and it defines whether different sources are involved in generating the electrical activity of the two scalp maps. If the same sources are involved, then the scalp topography will be very similar there. They might change in the how strong the color is, but the distribution will be very similar there. If the different sources are involved, then the distribution will be different. And how you can do this test, compute the test whether these two maps are okay, or calculating this. Earlier I showed you where it is. You can do usually permutation test there. So permutation test, it's a very straightforward. If you have a suppose within subject two conditions, so you have in your raw actual data give you condition 1 global field power, condition 2 global field power. Now you want to find out how they are different, right? Because the statistic is nonlinear, you cannot calculate an individual level and then compare a t-test. No, that's not possible here. So what you can do, you randomly assign shuffle condition 1 and condition 2 there. So just shuffling your data, shuffling your condition, not the data, shuffling the label there, and then calculate the global field power again. There, you get a value. You do this shuffling many times, whole procedures. If you have a n number of participants, you can do it 2 to the power n, there, which is usually a large number. You don't need to do that. Usually around 2 to 5,000 shuffling should be good enough there. So, every time you shuffle, you calculate the global field power, calculate the differences there, or global map dissimilarity, calculate the GMD or GFP, and then you see whether your shuffled sequence there, because if you do a sufficient number of shuffling, then you get a distribution of your shuffled values, or the global or the values of GFP or values of GMD of the shuffled sequence. You also have the actual your raw data as well. What is the actual GFP difference or GMD difference at the GMD for your raw data or actual data, and then you calculate simply exact probability. So, you have a 5,000 values for the shuffle, provided because when you are doing shuffling your null hypothesis is two conditions that don't differ there, and now you can calculate the exact probability. So, what is the probability of getting this GFP given the null hypothesis is true, and that you can calculate your window or this time point whether GFP is statistically significantly different between the two conditions by this permutation test. Okay. Okay. So, now next to the last section of the ERP analysis, that is the ERP source analysis, which is again is possibly most mathematically heavy there, but I kept it as non-technical as possible. But if you are interested, you are engineers there, I can tell you, if you are interested in methodological advancement, how to model the tissue, brain tissue, or how to calculate how the current passes through the volume, I can give you or the appropriate references. The first I like to tell you, this is my personal disclaimer, that because I am personally quite skeptical about ERP localization there, and in my view, I mean, although I am mentioning to you here telling you, but usually I do not recommend source analysis someone doing EEG ERP first time, no. So, it is for me, it is like metaphorically, I don't like to give a knife to young children, right? Why? Although knife can be a very useful tool, but once he has gathered or gained sufficient manual dexterity and also developed kind of rational thinking, then only he or she would be suitable enough to make the best use of this tool. So, similarly, in my view, ERP localization source reconstruction is a very mathematically advanced. You can always get some results there. There is a lot of softwares there, they would give you some results surely, but you have has to be always very careful about not only to interpret the results, but also what data you are inputting in there, and how, because all of these methods you would find they require a lot of assumptions, a lot of parameters to fix, how to choose those parameters in a right way. Otherwise, we say garbage in, garbage out. So, it is very useful, you would see, but I personally have reservations, but why still I am talking about them. The first is localization is actually one of the principal aims of cognitive neuroscience. That is the not just the cognitive neuroscience, it is the principal way our brain functions to some extent there. Not localization, but for the desire to localize there, because localization gives us an easier explanation, one brain region, one function there, and that is a very easy way to explain. And if you look into it, that is how, to be honest, this neuroscience or its primitive versions of neuroscience started there, when I think late 18th and 19th century, I do not know whether you know this, called phrenology, started by Austrian guy. So, he came up with an idea that he could predict your personality just by touching your skull, for the bump of your skull. It's a certain bump, or how the way your skull here, certain bump would associate it with certain personality. So, he has a very nice map there, which depending on how is associated with a certain type of personality or thinking style or attributes there. So, this is again a reductionist approach. So, that is the thing, that is the biggest I would say the catch of the localization, because it is a very reductionist, and the science is reductionism there. We want to reduce everything to explain by a single quantity there. Brain is a complex, but if you can describe or associate a complex function with one brain region, naturally you have achieved a great deal in terms of explanatory power there. So, the story I was telling, this phrenology, which was very powerful for many years there, predicting people's personality by touching the head there with a detailed map used to have. If you search in the Google, you will find phrenology. It was very powerful, but then later on it fell into disrepute because there is no science behind it. But afterwards, in late 19th century, actually the modern birth of neurology is also started by a kind of localizations. I don't know whether you have you heard the called Broca's region? Anyone? Broca's region? Okay, so Broca's region is a region in the frontal part in the brain, primarily the left there, which is relevant for language production. So, means if I have a stroke here, hopefully not now or not in the future, or if anyone suffered a stroke here which reduces the blood flow in the Broca's region, then he or she would lose the ability to speak there. And this particular, I mean, now we know that because this is the region which reasonably controls for the production of speech. In 19th century, the French neurologist Paul Broca, so he had a patient, adult patient, but who could only speak one word called tan. Everything he should say tan. And then after I think he died, then Broca, when he was analyzing, he realized there is a big damage on the left frontal part of his brain there, and that's how it is called the Broca's region, because Paul Broca discovered. So, now here you can see why I am telling all these things. Now, speaking language is a very complex faculty, right, and there is a certain region in the brain, for some reason it was damaged, and that disturbed or just impaired a very complex faculty, that is speech there. So, that is where kind of modern birth of neurology or localization there. And after Broca, then came another one, German neurosurgeon Wernicke, and he found that if there is a brain damage in a slightly back temporal regions, then you would be able to speak, but you will not make any sense. So, then the language comprehension region, so that was called the Wernicke's region. So, those are the regions are responsible for language comprehension, to make meaning out of it. Also, while you say it meaningfully. So, then afterwards, so these are the kind of one of the primary examples of localization example there, how the certain brain regions perform certain functions. And another aspect which was quite crucial those days, that we call it double dissociation, means if you have two brain functions, or if you have, suppose in these cases, if you have some damage in the Broca's region, you would be still might be able to understand, but you will not be able to produce. If you have a deficits or damage in the Wernicke's region there, you would be able to speak, but your meaning is gone. So, this dissociation between one function is impaired while other is intact and vice versa. So, that gives rise to this aspect of localization and modularity that the different brain regions acting as a modular way. So, when those region is damaged, because it is acting as a module, it does not disturb the other brain regions. So, that is the modern birth, we call it neuropsychology or neurology there. And then later on there has been a lot of very good research has been found and shown as supporting these localizations there. But then afterwards fMRI came, which is the functional magnetic resonance imaging, because of its unprecedented spatial accuracy, at least according to the the currently available methods there, it can give you a very reasonably precise picture of brain activations occurring at a local scale. So, what primarily researchers were trying to do, they were doing a lot of brain scanning while participants performing from simple to complex tasks, and they try to highlight or isolate where in the brain the hotspot, means where in the brain certain regions get activated, means need more oxygen while performing this particular task. So, that is the kind of currency, I would say, these localizations was very dominant over many years. So, that is why there is a big body of literature available to relate certain brain regions and host of cognitive functions there. Now, when you do record an EEG, we talked about it as an excellent temporal resolution, but if we cannot localize the brain activities, then still our interpretation is less than complete, because we still cannot talk about where in the brain this is happening. And unless we can tell where in the brain it is happening, we can only provide some kind of hand waving explanation. So, that was the one of the reason or driving reason why the researchers working in the EEG field or somehow have to invest how we can get a better localizations or how we can localize the activity from the scalp space to the source space there. So, that is the thing that, well, you want to compare your findings with others. Others means there is a big body of literature using fMRI or using primarily the lesion studies where the patient suffered from stroke at a particular region and then they are studying the deficits there. So, the first or two foremost reasons are that you want to interpret your data with more confidence, and the second is related, you want to compare your results with other the big body of existing literature. And the third is which is somehow practical, that we know that EEG localizations current way is less than accurate, you will see, but it can be improved if you have an MRI of the participant there. So, if you have an access to fMRI or even you can combine with MEG, your spatial accuracy would be improved. And the fourth is localization is reasonable, okay, if you are expecting a few sources, few dipoles. And the last one, which is rather unhealthy, I would say, there everybody does it. There, I would not say that is the best reason to do it, but as you know, when you are in the system, you have to play by its rules there. So, if you want to make a kind of stronger impact there into the field, then you really have to go from at some point sensor space to the source space there. Okay. So, from source, so now let us go back to the looking from the other directions. Suppose we talked about a lot that activities at any electrode is a mixture of activities of many sources. Take a very simple example here. So, this is the head scalp and this is a very simplistic brain. So, here there are three sources, three different orientations of dipole, and you have three electrodes, E1, E2 and E3, very simplistic. So, each electrode is, and each source has these different waveforms, how they are active there. But what you get from the scalp, you do not have access to only one source only. You are picking up, because each electrode is picking up projected activities from each source, and they are usually linearly superimposed. So, linear superposition. So, definitely this source would have more activity from S3, but it also has activity from S1 and S2 there. Like here A1, it has activity from 1, 2, 3 all, and similarly 3 activity from 1 to 3. And how these activities are mixed together? By certain weights there. So, that is a standard linear assumption. So, what you have, you do not have this access to the source waveform there, you have only the raw data, which is the potential, which is the linear combination of these 3. This is also linear combination of these 3, this is also linear combination of these 3 there. Now, the forward problem is, suppose you know exactly the location and the strength of the sources, location, strength and orientation, suppose you know. Then if you know these things, our task is, given these sources, what would be the scalp waveforms? That is a forward problem, that is a mathematical problem, and that can be solved there. Here we know where are the neural sources are located, what are their strength, what are the orientations, and the task is, knowing these individual sources, dipoles, how can I calculate what would be my EEG potential recorded at the scalp. This is a simple biomagnetics problem, because you have to, we will see, once you know the location and strength of the problem, you want to see how current propagates in the brain, then in the tissues there, and then finally through the skull and recorded at the scalp there. So, that is based on certain assumptions, you can just analytically solve there. So, that is a forward problem, less problematic. But the inverse problem, that is what usually we are faced with, that we only have activities at the electrode level. So, how can we find out activities at the source level? So, forward is going from source to the electrode space, inverse is from the electrode space to the source space there. And in order to solve the inverse problem, actually we have to solve the forward problem first. So, forward problem is, in a pretty simpler way, given a dipole in a specific region with a specific orientation, what will be the field potential distribution at the scalp, means what will be its topological map there. Very simple, you put a dipole somewhere on the scalp, somewhere on the brain there. So, this is my only one brain source there, and what will be the potential distribution over the scalp there. And as I mentioned, this is a mathematical problem, can be solved. So, it has a unique solution, and it can be solved without knowing an EEG there. Only you need to know where in the brain you are allocating that source, with what orientation, what layer. So, you just have to configure the where your input you are allocating that neural source. It can be analytically solved, what EEG you will get if there is only one source. And accuracy of this estimation depends on several things, how you want to model your head. If you, from the mathematically simplest one is assuming the head as a sphere, because then you get a very clear analytical solutions there. But slightly more accurate model estimation you will get if you use a numerical modeling there, using or incorporating the geometry of the scalp there, and also the density of the individual brain tissue, density of the cerebral spinal fluid, and so forth. Because in any case, you have to model how, when the current flows through the brain, flows through your the region between the brain and the scalp there. So, this is like literally like biomagnetism there. So, here if the when you have, and how you can get those informations by MRI there, because MRI gives you a very nice informations about the individual densities, and you assume that within a certain regions your tissues are homogeneous and isotropic there, so that the tissue's conductive properties do not change. On whenever there is a you can use this boundary element methods. So, whenever you go from one regions to another regions, the boundary, in order to smoothen the boundary or transition, use a triangle. That is a simple boundary element methods. You can have a more advanced finite difference method. Then instead of a triangle, you use a what is it called, I think tetrahedra, more of a complex geometry there, just to get a more smooth approximation there. So, the idea is that here the principle is the same. You allocate a source, you solve analytical model, you fit your brain, either using what kind of model you use, depending on whether it's spherical spell model, but they will be more erroneous. You can use a boundary element model or the finite difference model or finite element model there, and then you solve your problem or get a solution there. So, that would be your forward solution. In standard cases, or in most cases, when you do record your EEG, you do not have MRI there. Here individual MRI, if you have each person's MRI, head MRI, you can get it, then the solution accuracy is much better, because your head shape is very different from my head shape, and that is why how the current propagates in your head would be different from my head, and that depends on not only your head shape, your brain folding, your resistivity, your tissue density, your cerebral spinal fluid, and those information you can get from individual MRI. So, that is why you get a much better approximation or get better forward model solution when you have individual MR images are available. But in standard practices, we do not always have MR images there. So, what you can do if you want to do the go for solve forward model, there are called average template. So, there is an average head model is available there. So, as if you are assuming that everybody has the same head, same head kind of head shape, same brain shape, brain folding, same density, and so forth. So, you are averaging. So, naturally, when you are, instead of individualizing, you are considering an average template, your approximation would be slightly erroneous, but you can do that. Yes. No, here you are assuming there is only one source. So, only one you are putting, you are not considering, you are just putting only one source. That is a point source, that is right. Only putting only one source at the one locations there, that is right. So, you are not doing any distributed, that will come later, distributed sources. You are just putting only one dipole, and there you already decided where you want to put your dipole. So, that is where the forward model. So, you decide, suppose you are doing a motor task there, you are putting a dipole in the motor cortex, premotor cortex, and based on the previous literature, you put at a very specific locations with a specific orientation. And what a forward model does is primarily, after you solve these equations, it would give you what would be the EEG if someone records from the scalp, given there is only one source in the brain. So, that is the forward model, and this estimation would be better if you have the MR image of individual participant. So, take an example of scalp distributions there. If you press a very single superficial dipole here, and then the scalp distributions are usually quite focused there. So, here the distribution okay, it can change a bit if the dipole is either rotated or shifted. Oh, sorry, sir, I got a little bit fast, but it's just a very general, sir. Yeah, so I mean, as I said, how much we know? We know quite a bit if you have the individual MR images there. So then it would help us to solve you the forward model better, because then you are trying, because you have a better model of volume conduction, how the current would going to flow in the volume, because you need to know the density isotropic, because although you are assuming the in small regions are isotropic, but you still have a good idea from the MR images, the tissue density, the folding of the structures, because that will help you about the flow of the current in the volume there. In the, that's right, because also you have also the density of the cerebrospinal fluid, because there is a thin layer between the outer layer of the brain and the lower layer of the scalp. That's the CSF. You need you get the density of the CSF if you want to model that, because before it reaches at the scalp, the signal has to propagate all the complicated geometrical structure and finally some fluid, and then reach the scalp there. So you have as far as I know, you have a decent good approximation if you have the individual MR images, provided you know where the brain sources are located. So this is the forward model. So this is not fitting the data. This is, you know, as if where the brain sources are located. And you will see here, so this is just putting a dipole, okay, at a much superficial, means much higher, very at the core, outer layer of the cortex. But if the dipole is deeper, that creates a much broader scalp distribution there. And then the deeper the dipole is, much difficult to localize with precision there. And also it is quite hard to distinguish from broadly distributed superficial activity, and that's why if you have, suppose I gave a 2 example, this is called error related negativity, and which is often generated in anterior cingulate cortex. This is usually what happens when you are, I think I mentioned to you, when you are suppose learned a task, simple motor task, and then if you made a mistake, your brain would immediately generates a negative ERP signal. That's why it's called error related negativity. And this is usually located in the anterior cingulate cortex. So this is usually, if you dig a hole here deeper, this is midfrontal area, and that's much deeper regions in the brain there, which is quite difficult, not that easy to localize from the EEG. So anyway, that's about still a forward model. You can localize this dipole reasonably well as long as you have fewer dipoles. Suppose here just only 2 dipoles there, as long as these dipoles are reasonably far apart there. If the dipoles are somehow pretty close, or also dipoles are on the same axis, then things become even difficult even for this simple case there. So as the number of dipole increases, definitely the likelihood of a difficult to localize get much difficult there, it or becomes greater. So that's the forward problem. But now comes the inverse problem, which is the more difficult one. So now this, what you have, you do not have access to the location of individual sources there. What you have, raw data, which is the brain responses from different locations. Now given a topological map there, what are the most likely orientations, locations and magnitudes of brain sources that give rise to the observed pattern? So what you primarily trying to achieve, so this is my given distribution of the potentials for EEG or field for the MEG, where in the brain sources are active there, what are their orientations, what are their magnitudes, where are they located, that altogether give rise to this distribution that I have, and that is called the inverse problem there. So you somehow going backwards from the scalp, from the sensor space to the source space there. And the problem is there is no unique solution there, because it is an ill posed problem there, because for the same scalp distribution you can have infinite number of solutions mathematically possible, which give rise to the same solutions. So, it is the problem earlier I mentioned in a slightly different context, same effect, but various causes, many causes. So, you cannot separate which cause is the unique one which give you this unique distribution, or which gives you the potential field that you are recording there. I think I will continue after that. I will give it a break here there. Okay. So, on this aspect a bit more about inverse problem. Okay. So, yeah, so in the morning session we are talking about how to design a better ERP experiments and how to extract or estimate different kind of measures to quantify ERP waveforms, both in the time domain or in the amplitude domain. But those analyses were done at individual electrode level. So, you measure a mean amplitude at a particular electrode. But now this session we will talk about the different ways you analyze all the electrodes together, because nowadays we measure not just from few locations, but over a handful of locations, and from 16 channel, 20 channel, 30 channel, 32, 64 there. So, it's kind of good reasonable spatial sampling over the scalp. So, in addition to applying your measures or analysis at the individual electrode level, so we are also interested how we can analyze all the electrodes together.
হ্যালো 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 নয়েজ আছে ঠিকঠাক হ্যালো 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 চেক হ্যালো হ্যালো অডিও নেই হ্যালো হ্যালো নয়েজ হ্যালো 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 ঠিক আছে আসছে হ্যালো 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 ঠিক আছে বলছো হ্যালো না না স্পিকারের কথা বলছি না ওখানে গ করছে নাকি হ্যালো 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 করছে
about the main essence of the inverse problem, that how to go from the sensor space or electrode space to the source space, because distribution of the source activities, that's your aim of source reconstruction. But in order to solve the inverse problem, we talked that we have to first solve the forward problem, and I talked about these things quite a bit in different ways, showing different figures, that how the brain activities or electrical brain activities recorded from the brain scalp are generated in the brain. So you have the radial, okay, the dipoles, you have the oblique, we didn't mention that, but doesn't matter, and that's a tangential dipole where you have this in the sulci, in the fold there. And because the pyramidal cell, which is the primary source of the electrical activities generated in the scalp, they are always perpendicular to the surface. So these are the radial dipoles and these are the tangential dipole. So if you recall, EEG sees both but sees it better. MEEG is blind to radial and primarily sensitive to the tangential there. And since each of the neuronal sources can be approximated by a small dipole, and because the pyramidal cell are geometrically aligned in a very parallel fashion, so mathematically you can combine them as an equivalent current dipole there. So it's a mathematical concept, ECD we call it, equivalent current dipole, but it's very useful there to sum up the activities of one small cortical patch there. So that's, you have the radial, you have the tangential there. And what you primarily want to achieve is nothing but from the scalp space how to get a better information about the ECD there, because we cannot model or recover activities at individual neuron level from the EEG, but we can talk about over a reasonable patch, cortical patch, which is modeled by the ECD. So one approach of this inverse problem is called equivalent current dipole approach. It's introduced by these two guys, Michael Berg and Sheg. This is a 1990 paper, and then afterwards they realized, oh, there is a good opportunity for business, because researchers want to find out sources, but they don't have the ability to do all the programming, especially those days. So then they left academia and found a company called the BISA, Brain Electrical Source Analysis, which is primarily they started to make a very user-friendly software for source reconstruction, but later on they provide a host of EEG processing there. Very expensive software, but they're okay. I mean, that's where before that they were in academia, and their approach is called the ECD approach. What you do here primarily, you first start allocating a fixed number of dipoles. Say here it should be not too many there, so fewer than 10. And in these dipoles you have to decide about their location and their orientation there, but their magnitude, so dipole moment can vary there. And then you calculate the forward solutions there, provided or given this 10 number of dipoles there, and then you calculate, once you solve the forward solutions, you get the scalp distribution, means the model EEG, this EEG as produced by this given number of dipoles. Now you have your raw EEG. So you find what is your model, what output your model produce. In this case is this the output of the forward problem, and then you have an actual raw data, and you calculate your model error there. So you compare your forward solution with the observed scalp distribution then. And then what you do, depending on what error you get, you start fine tuning your parameter. Fine tuning your parameter in the sense of this what locations and orientations there, because you start at somewhere, you find a prediction error, prediction based by the model, based on the forward model, and then you start playing around there, and then you stop somewhere when you iterate at your iteration stops once you do not achieve any better approximation and once you stop there, that would be your given or that is the estimated locations, orientations of the dipole there. So now you can see here you already have to have a good starting point, because there is no one way self-organized way of finding the dipole locations, and that is usually guided by what type of research question you are doing it, what other people have found there. Accordingly you place your dipole, because suppose if your experiment involves a very elementary visual stimuli, or suppose face, you expect there will be activities in the fusiform face areas there. So you put a dipole there. So you are not putting a dipole arbitrarily somewhere in the brain. So you are constraining already your solution getting close to the actual scalp distribution there. But nevertheless, you can see here, if you have each dipole as a 5 parameters plus the magnitude, which you are afterwards assuming, you have a location 3 parameters, you have orientation 2 parameters, and then magnitude 1 parameter. Important point is, all these 3 parameters you have to first tell your model there. So there is a lot of subjective decision, but you have to make in order to get the best out of this process, you have to start at a reasonable point, otherwise your model do not converge if you just arbitrarily or randomly select, because there is no way you have convergence. But if it is guided by previous research, once you roughly know where you are expecting your dipole and approximately a few, then you can get a reasonable approximation there. So here what it shows here is this experiment is not important which experiment it is here. So here you can see at this time period these dipoles are approximated here. Another time periods there are some additional dipoles appear, and then later on a little bit reorientation of the dipole. And naturally, because it's a model, so every time you fit you can calculate how much variance is explained. So it's a goodness of fit you get there. So it's a simple kind of approach, but serves the purpose at the beginning quite well. Just simple dipole approximation by equivalent current dipole steps. So the steps are, just to tell you, we have a starting process, starting model of dipole locations. There is the current model of dipole location, sorry, I don't know, it should be I locations and orientations, and then you solve the forward model and then you distribute. You find what your model, forward model gives you, or solution, what EEG it produces, you compare it with the real EEG there. So that's for the comparisons. You calculate the residual variance, you make some small adjustment to the model there, so that your model would come up with a better fit. Better fit means less residual variance there. All points, yes, all 32, 64, yes, there, because as you know in the scalp, even if its electrodes are far apart, but it's still picking up some activities from the from your location. So yes, you have to observe the whole scalp there. So ECD was quite powerful, because that's a kind of one of the very few softwares available to the users there who can apply source reconstruction techniques. So it is quite popular, still people use it there, but it is very much dependent on the operator there, because you need to first choose quite a few free parameters there, and means there is also the whole procedures can be biased by expectation as well. And also it's quite difficult to assess the accuracy of solutions, because you have 5 free parameters, and if you have a 6 dipole you have 30 parameters there. So it's a lot of degrees of freedom, and when one parameter is somehow incorrect, other variables can also change slightly to maintain low residual variance there. And on the top of it, if you have a data noisy or errors in the forward, or if there is a problem in your forward problem solution, then even if it's a substantially wrong solution, can also lead to a lower residual variance than a correct solution. It's mainly because your forward problem is wrong there. So you are literally working on a wrong solution but you might still end up with a low residual variance. So here low residual variance would not tell you anything about the actual locations or actual correct appropriateness of the solution there. As I mentioned, the BISA is the first okay, that's where the company is formed. Then if you are, I talked about EEG lab. Yes, EEG lab also provides you, okay, the ECD approach, and another dominant toolbox, field trip, MATLAB based, that also offer you or allow you to do equivalent current dipole. Kind of my take is there. I mean, definitely different people, depending on, okay, who they work with or what software they use, they might have a different viewpoint. But my view is, when only one dipole is present, it performs reasonably well, because you have a fewer free parameters there. But when there are more dipoles, when you are dealing with a more of a complex situations, then problems start creeping in. So then you have to be really careful about how much you can trust this approach. Only fewer dipoles can give you reasonable approximation there. An alternative to this kind of very fewer or ECD is, we call it distributed sources there. So you are not assuming only one currents, only one dipole, you are assuming there's lots of sources there. We call it distributed source reconstruction. So it means situation, the formulation is the same. So there are many sources, all distributed all over the brain, but at any moment in time, at any electrode, the voltage value is again a linear combination, weighted linear combination of all your different sources there. So its formulation is the same. So you have a different weights of all these sources there. So you can express in I mean, voltage at a given electrode as a sum of voltage of at each sources multiplied by the weight of for the each source unique to the individual electrode. So now if you formulate in this very general framework there, so here each weight W, that primarily depends on the orientation of source with respect to the electrode and conductivities of brain, skull, white matter, gray matter, cerebral spinal fluid, and so forth there. So if you take a simple, what you want to do here primarily, so that's your observed signal, that's the weight matrix, and this is your source. Very simple formulation. What you want to take the inverse there. It's a similar formulation like ICA I showed you earlier. So you want to, your signal is a kind of linear mixture of all distributed sources. Here definitely ICA is a number of source or independent component is constrained or equal to the number of channels, but here you can have thousands of sources, although you are measuring only from 32 or 64 channels. W is complex. So now the problem is here, naturally it is you cannot take a proper inverse, because you have only fewer channels and you are assuming a few thousand sources there. So you want to somehow apply some kind of minimization. So it boils down to finally a kind of minimization problem. And also there are certain aspects there, which is, I mean, just to tell you, okay, I mean, you don't need to worry too much on that. There are certain sources which is suppose here. Suppose this dipole is pointing towards here, this dipole pointing towards there, so then they will cancel each other out there. So there you can't do too much with it in this approach, just to let you, I mean, you should be aware of that. So this, once you do, it's a kind of, you have to do kind of optimizations, and now when you talk about optimization, there are different methods of optimizations. I just highlighted some very briefly here. You can do minimum norm estimate there, which is pretty common optimization technique there, but minimum norm is used quite widely, but it doesn't give you the kind of solutions, kind of best solutions is not guaranteed. And also minimum norm is quite biased against the sources which are rather deep there, because minimum norm is weighted against stronger sources as well, and stronger sources are, and the deep sources really have to be quite strong to have much impact at the scalp there. There is a one way, kind of, you can change your weight depending on the depth there, that you can do, okay, but that also some suffer from, okay, some other problems. One approach which is very popular, possibly I would say popular mainly because The software is very easy to implement, easy to be used by the researchers. There, you don't need to worry too much on the mathematics. It's kind of plug and play. It's called low resolution electromagnetic topography. So what this offer the solution based on the which is maximally smooth there. And as far as I know, there, so this software gives you very nice fancy figures like fMRI like activations there, because what it primarily does, I mean, at the output from the 64 channels, you get a matrix of, depending on, I think Loretta these days, you have a 6,000 voxels there, and each voxel has an intensity there, and each voxel primarily is a dipole. That's what is model. So you are literally decomposing your EEG signal, which is recorded from the scalp, into 6,000 small dipoles there, and this, each of the 6,000 has x, y and z coordinate, which tells you where exactly in the brain this voxel is located. Similar like fMRI data there, you get for fMRI the voxel intensity, where you know exactly where this individual voxel is located. Only the difference is, usually fMRI, each voxel you can get as small as a millimeter cube. I think the Loretta is around 10 or 15 millimeter cube, so it's much larger there. But what you get primarily is a kind of similar idea, that's distributed sources, and each distributed sources you know where exactly it is located. Huh? You can do also for image as well, yes. There. Only thing is, I cannot tell you at this moment what additional parameter, or whether in the settings you have to choose anything different or not there, but the software allows you to do that. So other types of distributed source imaging, okay, I mean, says minimum norm estimate I mentioned, the brainstorm, these are different software, but they all rely on, okay, one type or another of distributed source imaging there. So these are all free software actually. I think all the softwares are free, so you can try and play around with the software. So advantage is, these are most of distributed source imaging, they're usually quite fast, so you don't need to do any kind of iteration there like you have to do for ECD there, and also can be applied for much fewer data points. And third, which is possibly more practically interesting or appealing, it can produce fMRI like activation maps there. So literally you can assign the voxels intensity and project it on, not on the scalp, on the brain surface there. And usually you don't have that many free parameters to choose there. Disadvantages, okay, there, because you have so many voxels, you are not talking about a few dipoles anymore, you have a 6,000 voxels there. So naturally, if you remember in the morning we talk about multiple comparison problem, so you would have to be very careful about claiming about significant activation. So for example, if you have a condition 1 and condition B, and if you contrast between condition A and B, if you do it at each voxel, then it doesn't matter whether some voxel gives you p-value lower than 0.05, because you are comparing a few thousand times there. So you really have to be very careful about here applying false discovery rate or applying some kind of permutation statistic and then applying false discovery rate to control for the multiple comparison problem. So just to give an idea, okay, here, so this is the minimum M&E because we did it very simple. So here again this experiment post details is not important here. So this is two different conditions, condition A and condition B here. I mean, I can tell you this is one case is you are expected, one other case is the sequence is unexpected, and you see there is a strong ERP differences, right. So this is a ERP, okay, and here you can see it's kind of N1 component we say, and then we feed this data and try to find out where in the brain this effect is explained there. So this is the scalp map. If you look at the scalp topography, it gives a very wide region of the prefrontal cortex there. It doesn't tell you where exactly. That's natural because we know the the functional, the topographical localizations, it's usually broad and it's very difficult to say exactly where in the brain. But if you feed this data into source reconstructions using, I think we use a minimum norm estimate there, and we found after doing proper statistical comparisons, the difference is primarily here located. You can see here, you can get a very fMRI-like map there from the EEG data. So it tells you that activities are primarily located. This is, again, details are not important. It's inferior frontal gyrus, because each voxels there has a unique XYZ map, and that from XYZ you can, because there is an atlas. They use the Montreal atlas, or also you can have a Talairach atlas, where each voxels have a unique XYZ map, and that corresponds to which Brodmann areas in the brain, where in the brain, so you can map it there. So that tells you that, okay, these regions in the brain, these activities somehow are associated with causing the differences between these two conditions. And now that gives you the kind of the license to some extent to talk about, okay, now in the literature what these brain regions are being associated, and then you can talk in a much more confidently explain what could possibly explain the involvement of these regions to explain these differences that you see on the ERP. If you only do it here, then you cannot precisely talk about one brain region per se. So that's where the reductionism comes into play. So once you identify a handful of brain regions, then your results are reasonably cleaner to interpret. You can link your findings with the previous literature much more easily. Okay. A more advanced there, which is I added just for the sake of completeness, is called the beamforming. Okay, this is more adaptive versions of distributed source imaging there. So here the weights, earlier weights are computed mainly on the electrodes there, but here the weights not just computed not only according to the physical electrode locations, but also according to the data recorded from these electrodes there. And here they use also the data covariance matrix there. So this is, we call it the beamforming approach, which can also be applied not just on the ERP domain but also on the individual frequency, because you have a cross-spectral matrix, so you can have literally source positions at individual frequency there. And since the weights here, because it's in weights you are kind of enable the adaptive changes of the weights, since the weights changes over time, frequency, participant, condition, so you have a much increased sensitivity for subtle features, individual frequency specific source reconstruction there. But anything you know, the more complex analysis you do, things often don't get so easier, because I didn't mention here, there is a lot of in between steps that if you want to do beamforming, again it involves a lot of free parameters to choose, and in my view and expertise, those parameters really need to be chosen very carefully. And on top, in order to exploit the beamforming to its full capacity, you need to have individualized MRI. If you do not have, your results are much more unstable. That's my experience there. And also it works better with MEG there, because the more the sensors, because here weights are adaptively vary and allocated onto the data that you get from the sensors, more sensors you have, the beamforming would give you the better kind of results. And MEG, you have a much more sensors, usually 306 sensors, than EEG you have a 60 or maximum 120 there. But beamforming is as far as I know, is the kind of the latest development in the source reconstruction literature. Okay, so source, in kind of my recommendation is you can see it's a kind of involved procedures. There is a lot of softwares are available these days. I mean, 20 years back, if you want to do, you have to literally have to write your own program to solve all this conduction problem. Now you don't need to worry possibly too much of the math there, because things, I mean, there are toolboxes there, they can do all this job for you there. But that means also, although it's kind of, if you treat it as a black box approach then you are more likely to end up with an inaccurate approximation, because you need to know exactly what you are doing it there. So it's quite involved procedures, so it should be exercised with caution there, and only after once you feel more confident with EEG there. So I don't recommend you to go immediately source reconstruction once you have an EEG data. No, there. And if you also want to attempt kind of localizations, you should have an approach of hypothesis testing, because source reconstruction, it is not a good approach as an exploratory. No, there, because it involves so many complicated steps, parameter selections, you should not go in consider it as an exploratory approach there. So means you should not just take any two conditions as different as possible and say, oh, let's see where in the brain things are being different. No, that would be a very poor approach to address. So you should have, if you want to do source, it's better first to get a clear EEG or ERP signal differences in those established measures, and then you want to see where those measures differ, where in the brain they differ. So source reconstruction should not be your first line of approach. That's the point. So as I mentioned, feel free to play around with the localization in the context of discovery there, not a context of justification. And remember, the source localization techniques also lead to an hypothesis about a generated location, not a conclusion there. And very importantly, which we often forget, including ourselves, that once we get this kind of very appealing fMRI like picture, so it doesn't literally mean that this activity is generated exactly by this location. This is after all a mathematical approximation there. So these things that we forget, that there is a lot of assumptions are there from reaching from this stage to this stage. There is not much of assumption is needed to find this difference. This is the real raw data I got, and then simple averaging I find this. But in order to reach the source, there is a lots of intermediate steps there. It's an appealing surely, but we need to remember that we cannot confidently claim that these activities or this difference in the activity is generated by only this specific brain region there. I think, okay, so that's, I put some, the books there, and I also put some papers there. So I think I'll stop it here, but I'm very much open to, any question, queries, anything you may have, either today or overall, with experimental design or ERP analysis. Yes. So I'm free, just feel free to ask anything if you have any query, or if you want to share anything. Okay, so she asked, about in order to solve or in order to estimate the sources, we need to solve the forward problem, then, and how we can do that with the dipole. Yes, so to solve the inverse problem, we have to solve the forward problem first there, and for the dipoles, there, how we can select where I should put the dipoles, and that's as I mentioned there, because especially for ECD, which is crucially depend on the forward problem there. The choice of dipole should be based on your data, your experiment, previous literature, and on the top, not too many. So for example, if you are, and the dipole, as you know, what is primarily dipole is nothing but, or equivalent current dipole, there's some brain regions, a cortical patch there, which is actively involved with your task. If you because this dipole approximation problem, you are only expecting only few dipoles you can reliably estimate. So naturally, you also have to remember that you cannot expect a very complex task that you are considering that will be represented by only few dipoles at somewhere else, somewhere specific brain region. So if your task is complex there, you should not go into the ECD approach. No. Because you just simply, you expect you require many more brain regions to take part in taking part or to explain in your task there. So if you are looking at a very kind of simple task processing, so processing phase or processing certain visual object or processing a simple categorizations there, where you know that your experiment is very well controlled there you can expect the dipoles or a few dipoles to be active. But if you are talking about, okay, there I'm just telling, since you mentioned you're interested in the stress there, how we monitor stress or how we react, okay, then I do not expect that you expect or you don't expect that only a few dipoles would be relevant to give you the information that you're looking for there. So there it is more a distributed source processing. If you want to do distributed source reconstruction, that would be more relevant there. And actually I didn't show, there is a one figure in the printout there. We did it, let me see, actually I deleted it because it was not in the ERP, that's why I deleted it. It was a very complex task we did, very evil task kind of. So there is one particular conditions, we call it thought action coupling there. So thought action coupling means suppose there is a negative thought comes to your mind, and then you tend to feel that feeling something unpleasant about it there. Suppose if I ask you, if I am acting like an evil psychologist, ask you that tell me, okay, you can tell, no I should not, you're going to curse me. If you ask you that tell me that you hope that your mother or your brother will have a car accident, okay, and if you tell that, then if I ask you afterwards how do you feel, you feel that in normal circumstances we don't feel very good to say that. If I say, oh, my mother would have a car accident, but it is irrational if you think, because what I say should not have any consequence of increasing the likelihood of my mother getting involved in a car accident, right? Because it's just a thought. How should it, why should it influence the reality? But in certain individual there, I mean we all somehow feel a little bit unpleasant and we feel guilty a bit, why this bad thought we thought, so we all have a certain degree of guilt, but in certain individuals experience, or certain group of individuals experience this guilt much stronger, and those are usually suffering from obsessive compulsive disorder. So in someone who is an OCD, when they experience this kind of negative thought, they have an inflated responsibility. They think because I have thought this, it increases the likelihood of this thought becoming reality. So in a sense, in their brain, the thought and action get coupled there, and to a certain extent then they start behaving in order to neutralize the thought, then they start going in a doing something to suppress those activities, then they cannot, and this cycle goes on and on there. So we are interested in to understand what happened in the brain when thought gets coupled with an action. It is a reasonably complicated task. It's not showing a face and others. So there we found, using distributed source reconstructions there, when we compare between the or found the activations, it was a high density EEG study, and then we do distributed source, we found the activities are primarily found in the precuneus, which is a deep regions mostly in the parietal regions in the brain there. And not only that, we found that how strong the precuneus, it is related with how much guilt the participant felt afterwards there. So there is strong correlations between these voxel intensities. So we found the precuneus, we choose because there is a well defined brain regions precuneus, and we know that these group of voxels correspond to precuneus there. So then we calculated the voxel intensities in the precuneus region, and then we found this total overall mean intensity of the precuneus is correlated with how much guilt the participant felt, or the OCD people felt after after these visualizations or after telling this there. So there it shows that okay, in a complicated task there, you possibly would be much better off with the distributed source, not with the dipole there. But it's always important to establish some kind of relation. If you just say, oh, this brain region is more active, then the story is not complete. If you can show some kind of relationship, just as I give you an idea that we found this brain activity is related, correlated. The higher the activities, they found the higher the guilt ratings there. So this shows some kind of relationship between the brain activities and the behavioral responses. Then your story or the messages you want to convey becomes more convincing, rather than telling, oh, I found neural correlates of certain activities in certain brain or certain actions or thinking. It's always good to link brain and behavior there. Yes. EEG based biometric system. What is my opinion? Okay, that's a very good questions you ask. Okay, there. I mean, I showed a little bit at the beginning that not my research, someone else, other people's research, that how much the EEG and the patterns are under genetic control there. So means we show this with the twin study, or even we know, okay, although less explored, that in this how our brain rhythms, the patterns of the brain rhythms alpha theta in the sleep stage, this is very unique to us. The way my brain would respond in alpha theta band in the sleep is very much okay, kind of my signature. So it shows there is a potential or promise of EEG activity can be used as a fingerprinting, like a fingerprinting or brain printing individual. But how much is done? Not much there. Now you ask me what is my feeling. I'm feeling there is a good promise. Actually, there is a very good potential I feel there, that not just the brain oscillations, but also the brain connectivity, and on top we didn't talk about much, but how the different frequencies are connected with each other there. So means once you somehow created a diverse range of features there, then my feeling it might be in sometime in the future that we will have a much better understanding of coming up with this unique library of our own individual brain's library in terms of EEG, which might help in identifying individual. EEG is definitely very difficult because signal is very noisy there, and there has been a recent study actually which shows that you can do with fMRI quite a high accuracy there, fMRI connectivity pattern to identify individual there. I know there are some attempts of the EEG there, but not very impressive yet there, but I am hopeful there. And to be honest, if time permits, I like to learn myself, invest some time in these directions there. How many subjects you need to prove that? Okay, there is, okay, I mean, first of all, you need to prove not only, you have to prove within subject first, different conditions, because if you want to do, okay, I mean, discrimination, sensitivity, these are traditional statistical tests there. So you have to check it first whether how reliable it is, means whether I can tell by monitoring your brain that this is your brain, that is you, under different conditions there. So it's not just same condition, because that's the major challenge there, because EEG is also very sensitive to what you are doing currently there. But from the identification point of view, you do not want that. That is a noise. Whether you are in a good mood, whether in a bad mood, whether something, that should be a noise for user identification. User identification, the main task is to identify the user there. So that's a major challenge, even just to identify a user in various emotional, stressful other conditions there. And then comes discrimination, you from me there. So it's a laborious procedures there. I mean, I think with time we would get to see more of this, okay, of in this direction there, because I know this, the biometrics is a big field now, security wise there. I believe with time we would see more there. It's an interesting possibility there, because fMRI is, they showed already the promise, but fMRI is difficult to do. It's not portable. It's much more intensive. EEG is very easy to record, but then challenge also is possibly much more. Yes. How to select the subjects, that's right, I haven't talked about it. So I talked about experimental design, different types of analysis, that depends on your experimental aim there. If you are interested in studying the healthy brain there, so naturally you are looking for subjects who are not suffering from any neurological disease, not taking any medication. If they take any normal cold medication, those are all right, but not on regular medication, not on antidepressants, not on, I mean, neurologically healthy, that's what we say. You want to also keep a similar age range there. You do not want to mix suddenly with 80 with a 18-year-old there. So you want to keep the age range or age, kind of reasonably homogeneous within a group, but with a certain variations. Means it doesn't mean everybody should be 18 there. So we say between 18 and 35. So we expect the brain responses should be reasonably similar. And now next point is whether to mix male female or not. You can, but that depends on if you are interested in studying the gender differences there, then you have to have two groups. Whether the groups are similar age range, similar education, similar male, all are healthy, but they have one is male, one is female. I would say gender differences are there has been used to be a quite popular topic for many long time, but according to the current research, I haven't seen any kind of robust signature or differences between male and female. So unless you really have a very specific prediction and others, looking for gender differences is almost wasting your time there. You might find differences, but that would not survive in the long run, because so far as I know, big studies, they're collecting over the data over hundreds and thousands of participants, they didn't find much difference in the male and female brain, or whatever the difference is there is too small to claim any significant there. So in a sense means you can reasonably combine both male and female in a group usually, as long as their kind of numbers are matched there. So these are standard formation or formation of standard group. Now if for whatever it is you are looking for or targeting some specific participant there, you can also have specific participants. Suppose if you are interested in individual differences, say individual differences is a branch of psychology where you are still investigating healthy individual, but this healthy individual might share a certain personality traits there. For example, if you are interested in how someone who works better with stress there, so there are certain ways you measure their stress responses, and then you have a group 1 who has a score high on that there. Or you can think of, if you are using someone who has a higher working memory there. So there are certain tests to measure working memory. So you have a group with a high working memory, another group with a low working memory. Or there are other personality traits, lots of personality variables depending on what research question you are interested in. Those are irrelevant only if you are interested in addressing certain personality traits. Suppose I gave an example, OCD, because we are interested in studying how an individuals with OCD they differ. That's why we had to have a group which a high OCD there. So it's what your research group or what is your group of participants, that's pretty much determined by what is a research question there. Other than that, tend to be okay, because we are all in the kind of you are in a hospital, so we tend to primarily record from healthy individuals, healthy adults. If you happen to interest in the developmental aspects of how the children learns, then your group would be young children there. So that's the kind of commonsensical approach there. You want to have a certain variations in your group, but these variations should not increase or introduce a confound there. Confound in the sense, suppose if you have, here possible would not be, if you only targeting only, in the west, that might be a problem. Suppose if I'm doing a test only on people with a low IQ or someone sharing a certain characteristics which might impact the outcome, you do not want that naturally. So you want to have a kind of homogeneous, all healthy, with a reasonable age range, trying to somehow keep it right-handed, but at least you measure, or at least you have the information whether left-handed or right-handed there. So all, and yeah, kind of, unless you have a really specific questions about targeting specific individuals. Suppose someone, yesterday the person who supplies these EEG systems telling someone in the Bangalore they are working on how the children in the less privileged area they learn. So they are doing EEG, their group is children in the lower socioeconomic background there. So that's why the research question, that's why the participant group would be from those kind of strata or social strata. So it's all dependent on what you are addressing, what is your research question. If your research question is on infants, then you have to have your research participants would be infants there. If your research question is, most of the cases we are dealing with adults, so means mostly we call it there is a hypothesis, not hypothesis, an acronym called WAIRD. Means most of the brain imaging studies or psychological studies are based on first year psychology undergrads, primarily white, coming from a good reasonable economic background there. So white and from industrialized nations there. So that's happened to be a kind of opportunistic sample there, but it's up to your research questions whether, if you want to go recruit beyond IIT students, means just as you can imagine that most of the time when a neuroscience experiment done is done on the students there. So here also I believe if you want to do it here, it would be your students, your friend or other first year or second year, whoever you can get hold of there, and those are kind of standard there, as long as they're not on drugs, they're healthy, and as long as you have kept all the kind of standard, kind of tick all the boxes there, should be all right. Provided if you have a specific requirement of a specific target group, accordingly you form the group there. So naturally then also, there is these days a lot of studies are going on now, because earlier times we have done a lot of on the healthy adults. For the last 20 years or 30 years, we have done quite a bit on the younger children or infants, but we didn't know much about the elderly population there. So beyond 60, our knowledge was rather limited. So for the last 10 years, 15 years, there has been quite a bit of research interest, because nowadays we live much longer compared to 50 years back. So how the brains change and also compensates especially in the much later stage of the development, we call senior adults there. So if you happen to have an interest in studying a specific brain functions in the much later stage there, so then you have to have a much senior adult group. We did ourselves as well to learn, because that's where we realize there is quite a bit of gap in the literature there. Yes. any time of limb movement there. Okay, so this is somatosensory cortex and motor cortex there. C3, C4, FC3, FC4, yes. Effect of human mood there, yes, surely you do have. I mean, the mood is a very word which has a very diffuse actions. I mean, it's a kind of questions, you know. I mean, to be honest, if you want to find out effect on the brain out of a kind of a stimuli or a state, you'll always find, because especially mood, which is a very diffusive action there. And my simple answer is yes there. That is difficult to say. You cannot, if you say, okay, the effect of mood, whether on particular one, whether it is more on one brain regions than the others, or similar somatosensory, I don't think there has been much research is done, and I don't think that's very interesting. But what we know, that there are certain brain regions, they are more sensitive to the mood, and that's primarily, suppose, if we have to consider emotional circuitry, that's amygdala or hippocampus. So suppose that the research has been found that if you are in a depressed mood for a very long time, or if you are suffering from general anxiety or GAD, general anxiety disorder, you have an atrophy in the hippocampus. That means if there is literally the neuronal cell, okay, dying in the hippocampus. Or if your amygdala is hyperactive, I mean other way around, then you are more likely to suffer from anxiety there. That we know, because those regions are core, I mean amygdala especially, okay, regions in the emotional processing. Other cortical regions, how much they involve in the mood, I think that depends also on the task. There has been a lot of psychological experiments, including we ourselves did that. We showed that what emotion you are currently in, that colors your task processing, what task you would be processing there, and that colors different tasks in a different way, from the visual task, somatosensory task there. So for example, somatosensory task, I can give you one simple example here. Suppose if I take you, I mean there is no hill here, so suppose if there is a hill somewhere in slope there, and if I take you there at the bottom of the hill there and ask you, oh, what is the degree? You gave me a degree, 20 degree, right? And then if I take you in some other times, maybe at a different slope, now you are wearing a backpack, a little bit heavy backpack, ask you the same hill would be perceived by you would be much steeper there. So now you can see here, because here in this case you are now physically under physical exertion, physical stress, that changes a very simple task, which is just a slope perception, much more. It becomes much difficult. Now forget about the backpack. Now I can tell you, if I induce a very sad mood in you, you listen to a very sad music, you feel okay, kind of negative mood, and I take you to the same hill, that would appear much steeper there. So earlier the physical stress, and now I am talking about the emotional, they somehow taps, okay, or leads to the same effect. So it shows that, I mean this is one example, we showed in a different other effects on the effect of mood or effect of emotion there. So we know that traditionally we used to think that the cortical information processing or the cognitive tasks are rather immune from how you feel. So means our rational thinking, we used to think, oh, we are very rational, the way we decide is very rational. But in recent research over the last 20 years or so, it shows quite the contrary. So any decisions we take, even if we think we are very rational, but this is very much influenced by our affective state there. So from that point of view, I do predict or speculate that any mood induction would have a smear or diffuse some activities in the sensory motor cortex. Well, first biometric identification, you have to first check it. First problem is to identify the individual brain first. Okay, there. So this is what you're talking about. This is a social interactions there. Or if you want to say that, okay, I mean, you want to identify your own brain while you are waving hand, or you want to identify how I react to your hand wave. Okay. I don't think that. I mean, again, I do not know. And short answer is I do not know. But long answer is I doubt that would be okay. A very clear. That would give you the clear differences that you're looking for. There. That's my speculation. There. Because many factors are there. Okay. I mean, if you ever talk about your just hand waving, let me give you one example. That if you are a musician, your hand waving has a different cortical representations than my hand waving there. And not only that, if you are a string player, your hand would have a different representations opposed to suppose you are a pianist there. Because string players, they use their hand or fingers much more there compared to I am using my keyboard. They have a much finer representations required there. Huh? I know, but I don't think the discrimination or the sensitivity that you look for. I mean, you can try. I don't want to tell you should not try this, but I think you have to have a more kind of think about the paradigm a bit more, because this would not give you the clear differences in the signal that you are looking for, at least not in the EEG. Yes.
What kind of research is done in the direction, like is there any kind of pattern in EEG signals for similar kind of activities? For say we are watching some exciting movies or something like that. So is there any pattern observed in EEG signal for?
I mean, there's the whole field is like that. We always try to, whenever we do some new research, we try to see the results we found, how similar or different from other EEG studies. So surely there are patterns, but depend on the task. If the task is rather simple, naturally you will get a lot of more similar activations. If the task is different, you expect differences. And also these differences is not just because EEG, also because how you respond to the movies. In some cases, you find very similar activations. I can give you very landmark studies in fMRI there. So where the subjects are watching a movie. Actually, this is Clint Eastwood's this ugly. What is I forgot the full name. They measured the fMRI activations throughout, and they are interested in, despite your individual preferences, whether while you watch a complex stimuli like this, whether your brain responds in a systematic way. Because after all, end of the day, it's the same stimuli there. And they found yes, you also expect certain brain regions. They show stronger inter-subject correlations there. So means the brain responds in a very similar way as the movie progresses. Brains of across individuals. Now fMRI is definitely here you have a much better spatial resolution. In the EEG would be much more challenging there. But despite the challenge, you do find while listening to certain music or the movies, certain brain features are more consistently varying across individuals there. So the answer is yes, but this pattern is not unique there.
So the spatial pattern is more found than the temporal patterns?
Depends on, when you are looking for the consistency, you are looking for some spatial patterns or some features consistent across time there, right? So if you are only interested in looking for consistency at any moment in time, but also interested because each stimuli is dynamically unfolding, so you are also interested how much this stimuli or the pattern remains constant. Naturally, because the stimuli varies from time to time, your initial interest is whether some features which are common across participants are not there. But despite that, you also expect to find some temporal stability of certain patterns there. Okay, so if yes.
What should be
what should we include in consent form? Very practical now. Okay, there. Okay, it's a good question. Now the more nitty gritty. Okay, now you're doing experiment. We talked about who should be our participant and what should include consent form. Yeah, I can send you some of the sample consent form we use, although it varies from experiment to experiment. So there are two types of consent form. The first is the consent form for taking part in the experiment, and the second is for the EG. There. Because for the EG you are also adding, okay, in this case although there is no gel, I think yesterday's system, but sometimes because you are adding some substance so that's another factors. But otherwise you just describe your experiment. You try to be honest, but don't like to give too much information. There, I can show you on Monday as tradition standard small consent form there. Because why you should not give too much information? Because especially if you are interested in emotion and others, because we know the moment you give away too much of your experimental aims and full details, the participants might start behaving in a different way. There, we call it demand characteristics. Means if the participant knows that what kind of behavior or responses you are expecting them to do, then naturally that would interfere with your data there. But on the other hand, in most cases we are not deceiving our participant in most cases there. So you have to say briefly, this is the main aim of the experiment. We want to understand how the brain responds to a certain task there, and then you tell usually what the instruction, what you be presenting, and if they are pressing a button, what are the possible responses, some practice stimuli. Okay, all the informations would be anonymously recorded. That's usually, there is a world regulation is there. You have to record everything anonymously. You should not name a file by someone's name there. And the second is the participant has the right to withdraw from the experiment at any time. If they whatever feel uncomfortable, whatever reasons, they don't need to explain to you. They should have the right. You have to mention that in the consent form there. They also have the right to ask you to destroy the data there, and you also telling whether they would receive any cash or anything in return there. They know if there is any incentives there. I mean, I can show it to you some examples of consent forms, but that's very crucial, and they have to sign, and we have to keep this information. You are not supposed to destroy it. You have to keep it at least for a period of time, so that you know your participant consented. And at the end of it, there is a debrief form. In the debrief, you can talk a little bit more detail. What is the experiment saying? Because by the time already participants responded, they cannot change the data anymore. Then you can give more information if they're interested. But anyway, you have to give them some debrief there. Ethical approval. So this is whenever, okay, I mean this varies from institute to institute, because this experiment involves human subjects. You need to have some ethical approval there, and that is, you have to find out which institute you are working with, what is the procedure. Usually each institute has their own ethical committee there. Some institute, if suppose IIT, I don't know here, but I'm sure here it has. Some institute ethics work much smoother than others. Usually, suppose university, if they have some kind of tradition of doing this kind of experiments, their ethics is much smoother, because they know a lot of people, researchers are working. In some institute where experiments involving humans are not common, then they don't know much about ethics, so they make it unnecessarily very complicated there. But nevertheless, it should be there, and without ethical approval, we are not supposed to collect data from humans there. So that's against the World Declaration of Helsinki there. So that's, I think you have to find out what is the procedure for an institute. Should not be complicated, because you are not damaging any brain. You are not just taking electrodes into brain there. You are not giving any drug, hopefully not although that can be an interesting experiment there. There are some very nice landmark experiment done on application of ketamine to the brain there, and as long as you are dealing with you are not dealing with vulnerable populations, because usually ethical problem gets slightly complicated if your participants are coming from vulnerable, like children, young children, or patients there, or sometimes I don't do, but some other people do in the prisons. So those are vulnerable populations. Then it gets slightly complicated. Otherwise, if you are dealing with healthy human adults, EEG, non-invasive EEG, there is no ethical issues there. So ethical approval should be straightforward, but it depends on the procedure. Actual procedure depends on which institute you are working. Okay. So good. So that's it concludes the first week. So you have quite a bit of information, from practical to theoretical. So sleep on it there. Have a nice weekend there, and I will see you next Monday morning. And I don't know if there is an announcement there.